Hello. This lecture will cover pages 56 through 59 of my lecture notes. So please print those pages out and have them in front of you as I present this lecture on loop analysis, chapter 3D, loop analysis with current sources and dependent sources. Starting out, if you take a look at page 56, this is basically what we're going to look at. We're going to start out by loop analysis with current sources. Current sources in loop analysis present an opportunity to assign loop currents by inspection. It greatly reduces the analysis technique, and I'm going to show you what I mean. Up to now, we haven't had any current sources. If you take a look at the previous lecture, everything was a voltage source, and you're using Kirchhoff's voltage law as you go around the loops. You can look at examples 314, 315, and 316, and we're going to start looking at 314. It looks like this. I wrote it all out so it's easy to see. Here we have a circuit, but I want you to notice there's a current source right there. And they want you to find, in this case, V out, which is the voltage out here, and V1. Okay, and V1 is that point right there. Well, this isn't a voltage source. So if this was 2 millivolts, that would be 2 millivolts right there with reference to ground, but it's not. It's a current source. So by inspection, if you assign loop current I1 here and you assign loop current I2 here, notice that I1 is the only current that passes through that source. That's the key when you assign loop currents, when you have a current source. Make sure that that loop current is the only loop current that goes through that source. If that's the case, you can say right off the bat I1 is 2 milliamps. Greatly simplifies the problem. And now you just have one Kirchhoff's voltage law equation. Around loop 2, by Kirchhoff's voltage law, you start here, it's a resistance. Minus 2K, and you stop and think. Remember the technique? Minus 2K, you stop and think. What current? Well, the current lead current is I2 minus I1. Make sure you have the parentheses there. That's the total current through that resistor. And then you're at this point, plus 2 volts. And then you have a resistor here, minus 6K. You stop and think, what current? It's current I2 equals 0. That's not your standard form, but you get it in a standard form. Your system equations become this then. This equation yields this, and this equation up here in standard form yields this. There's your system equations in standard form right here. This is what I'm looking for. In some cases, I would just ask for the system equations. You solve for I2, you get 0.75 milliamps. And you can find V out once you know I2, 4.5 volts. Then to find V1, you just, around loop 1, Kirchhoff's voltage law. I started down here and I just went around this loop right here. And if you do that, there's the equation. Since I1 is 2 milliamps, which we already knew that up above, I2 we solved here. V1 is 10.5 volts. Straightforward problem. Let's take a look at problem example 315. What if you get a problem like this? Well, just I want you to do loop analysis. You have 2 current sources. I assigned I1 here. It's the only current that goes through that. So right away, I can say I1 is 4 milliamps. I assigned I2 in a clockwise direction here. It's the only current going through this. And right away you can see that I2 is minus 2 milliamps. All you have to do is go around this loop now. Really simplifies the problems when you have currents and you're doing loop analysis. Around loop 3, right here, by Kirchhoff's voltage law, we've done many of those right now. There's your equation. Make sure you can just write that equation, get it in a standard form, which I did. Here's your system equations. Throw it into a calculator. You can get I3. I get I3 right here, which just sets up the voltage drop plus to minus. This was a positive voltage here. I3 was a positive voltage, so we knew this was the right direction, so we got a plus to minus. So if you start here, you can just go negative 3 volts and go up the voltage drop here to get to this voltage V out. If you can't see that, well, basically use Kirchhoff's voltage law around this outer loop. That's what you're really doing. You're doing Kirchhoff's voltage law around that loop. You can see that V out is minus 1.5 volts. This problem really is a 5-minute problem if you look at it and understand the techniques. And then finally, example I wanted to do was 316 here. Looks like this. This is in the textbook. Notice we have a current source here and a current source there. You have to be careful how you assign these currents now. The way I chose currents is I picked this as I1, and it's the only current going through here. So right away I can say I1 is 2 milliamps. I2, I chose this as I2. And if I choose this as I2 and I make sure it's the only current that goes through this device, this current source, I can say I2 is 4 milliamps by inspection. Now, I can't assign I3 up here. If I assign this as I3, I'll have two currents going through here and I can't mess with I2 anymore. So look at my loop 3. I start at this point. I can't go through this guy and I can't go through that guy, but I have to pick up these additional elements. This one and this one. How can I pick up these additional elements right here? And I can't do this loop. Well, I start here and look at my loop. Let me do that again. It starts here and goes around here, comes straight down here, and comes up through that middle resistor and then back over. So start around that loop, and I want you to see how do I get, by Kirchhoff's voltage law, around loop 3. Plus 6, minus 1K, and then I think I3. Then here, minus 2K. Then you stop and think, and you really have to think. What currents go through there? I3 plus I2. Look at it. Then you come up through this one, minus 2K, and then you stop and think. And you really do have to think. What currents go through that resistor? I3 plus I2 minus I1. Yep. Then you do this, minus 1K. And what currents go through there? I3 minus I1 equals 0. You clean it up, you get that system equation. These two equations up here give you these two system equations. You solve for I3. I3 is a negative 0.667 milliamps. And you can find I out defined right here. I out, we already found out by looking up here. I out was equal to this right here, the sum of these currents here. Let's take a look where I out was. I out was assigned here in this direction, going down. That's the way the author assigned. Let's look up here. The author assigned it coming down. That's the way that here assigned it. That's the direction of I1 minus I2 minus I3. There's your answer. Good problem. If you can do a problem like this, you can do any of these problems with these current sources. But I want you to notice is these current sources really simplify things. 317. E317. Let's see what we got here. Let's see what we just finished up. 16. Let's do a couple more problems here in your book. E15, 16, and 17. Let's look at them real quick. This just takes a minute just to make sure you get it. Here's a learning assessment problem. They want you to find V out. I assign my loop currents very carefully. I1 is 4 milliamps. I'm almost done. You write one equation around loop 2. I called it I2 here, and you write the equation for using Kirchhoff's voltage law around this loop. You get this answer. Just using the techniques we've shown before. What about up here? About this problem here? There's only one current source, so I assigned, it's two current sources, I'm sorry. But I can assign that I1, it's the only current going through here, so I1 is 4 milliamps. I can assign this I2, it's the only current going through this. You end up with I2 is minus 2 milliamps. You need one equation for I3, and if I assign I3 like this, it doesn't interfere with that current source or that current source, so you have to write an equation around this loop equation. Solve the problems to get the answer. And down here, I assign current I1 in this direction. This was all I1. So if this is I1, it's gone through this current source, and it's going to be the only current going through that. You'll see this in a minute. So by inspection, I1 is minus 2 milliamps. So how do I assign I2? Well, I just said I can go around here and assign this loop current I2 and write an equation for it. It doesn't interfere with this. But how am I going to pick up these additional elements here? How am I going to pick up these two elements here? Because there's nothing gone through these yet. I3. I3 starts down here. Watch this. And goes up and does this whole outer loop. Let me do that again. Starts here, goes up, and I3 does a whole outer loop. I didn't mess with this source. You write an equation for I2 and I3. There's your three system equations. You can get your answer. What about loop analysis with dependent sources? You only have two problems to look at there. The reason being is because they're pretty straightforward. There's nothing new we're learning here. There's one example. Here's the problem. Basically, all we need to do is find V out. And notice there's a controlled voltage source here. No current sources, so we can't do anything by inspection. How do we handle that? You already know you're going to have one equation here, you're going to have another equation for here in that loop, and you need a third equation to define Vx. Notice they're all voltage sources in that problem. Around loop 1 by Kirchhoff's voltage law, you start down here. Okay, around this loop, I think you can get this equation without any problem now. Around loop 2 by Kirchhoff's voltage law, you start at this point, you go around this loop here, that equation, clean both of these up very carefully, get them in a standard form, and by inspection, you need that controlling variable Vx. Well, Vx is defined here, plus to minus, the author gives you that, Vx. So which current has to be the lead current if that's a positive voltage? Well, I1 does. So Vx is equal to I1 minus I2 times the 4K. Just Ohm's law. Once you start seeing this, these aren't bad. You write the three system equations in standard form and solve for I2 equal 1.5 milliamps. Then, if you know I2 is 1.5 milliamps plus to minus, it's a positive voltage, so that was the correct direction. V out is equal to that current times the 6K, and you get 9 volts for an answer here. Again, less than a 10-minute problem here to work this out. If you're spending 15 minutes on these problems, you just have to find the time, because you're going to need to do these problems in future courses and obviously through the rest of this course. And finally, let's look at 318. Looks like this. Notice there's a current source here. And there's a current source here. So if I assign loop current I1 and I make sure it's the only current passes through this, I can say I1 is equal to Vx over 2000. If I assign a loop current here and it's the only current that passes through this current source, I can say I2 equals 2 milliamps. Makes it real easy. Write an equation for I3, starting this point and going around this loop here. Write an equation for I3. There it is. I3 is 1.375 milliamps. Now you know you're going to need one more equation for Vx. You have a voltage-controlled current source here. What is V sub x? The author gives you Vx plus to minus. So you have to write an equation for that. Well, if you take a look, Pretty easy to see the lead current has to be I1 because it goes in the direction plus to minus. So the voltage drop there is I1 minus I2 times 4K. Clean that up, you can see that Vx is 8 volts. One equation, one unknown. And simply V out is simply equal to I3 times the 6K. There's your two answers. Oops, sorry about that. There's your two answers. Look at this and look at that circuit up there. Shouldn't have any problems with it. Just to make sure you understand this, here's a figure in the book. There's a couple figures in the book. It's pretty easy to see this. But here's a pretty complicated circuit. I might ask you to write just the system equations. How many equations do you need? Well, you need 4 right off the bat. 1, 2, 3, 4. I1 is the only current going through that current source. So right away you know I1 is equal to 4 milliamps. I2 is the only current going through this current source. So right away you know I2 is equal to Vx over 2K. So you have 1, 2, 3, 4 equations. You have to write a loop equation for 3. You need a loop equation for 4. But what is, then you need a couple more equations to get 6. You have 1, 2, 3, 4 equations. You need an equation here for I sub x, and you need an equation for V sub x, because there's two dependent sources. Well, what is I sub x? I sub x is the current in this direction, plus to minus. So if you take a look, I sub x is equal to I4 minus I2. You don't multiply it times a resistor. They want current here. The current is I4 minus I2 right there. That takes care of the fifth equation. The sixth equation is what's V sub x? V sub x is plus to minus, so the lead current has to be I3. V sub x is equal to I3 minus I1 times the 2K. They want voltage here, so you have to take it times the 2K. There's your two additional equations. We'll just skip over one more problem here. How many equations do you need to come up here with this? Okay. Well, you need 1, 2, 3, 4, 5, 6. 7 for a controlling variable Ix. 8 for a controlling variable Vx. Okay. And real quick, let's just take a look to see if you could tell me what Ix is. What's Ix in this problem? Take a look at that and tell me if you can see what Ix is equal to. Stop the video. Write the expression for Ix and write the expression for Vx. The controlling variables here and here. Ix is equal to I5 minus I6. I5 minus I6. There's your seventh equation. In your eighth equation, we need to find Vx. What's Vx equal to? Vx is equal to a negative I1 times 1K. And if you look in your note, you'll see these equations. You'll see all these equations in your book. There's example 319 in the book. A lot of examples here. Let's take a look at 319. They're the ones we just went over here. They're the ones we just went over on the next. We're on page 57 here of your lecture notes. So I guess what I wanted you to do is look at example 319 and write a couple equations. Not all of them, but look at this and write some equations. And then see if you're getting these equations up here. Not all of them, just do a couple of them. And then look at 320. We didn't look at that one, but look at example 320. and write a couple equations there. Not all of them, just a couple of them, and see if you get some of these equations they have in the book. $321. We looked at that. Write a few equations there and see if you can get those equations right there. You work problems out like this. Once you get your system of equations, you have to work these out with a program. You can't do this with manually. And then finally, I have a review or a quick summary on pages 58 and 59 of chapters 1, 2, and 3. I mean, this was the important equations in chapter 1. And you can solve for power here, or in this case you can solve for power over in this case right here pretty easily. Okay. Isolating power in terms of the let's see right here how we could take a look at this. This is something you should be able to do without too much of a problem. We say that the change in work is equal to the integral from T1 to T2 of power dt. Okay. You should be able to take this expression using your math techniques, and you should be able to find power by differentiating both sides. I didn't put all those equations down here, but with these three equations you can get anything we got in chapter 1. In chapter 2, I told you that Ohm's law and the power law and the passive sign convention and Kirchhoff's current law and Kirchhoff's voltage law, these 5 concepts were very important tools in electrical engineering. And with these 5 things right here, you probably do 70-75% of the analysis techniques you're going to run into. The voltage divider rule was important. The current divider rule was important. There's a passive sign convention. Here's a summary of resistance and conductance and what a short circuit looks like, an open circuit like, the voltage gain, Y to delta and delta Y transformations, and then the most important chapter 3 with nodal analysis. We worked lots of problems. Talked about how to handle supernodes. And with loop analysis, worked lots of problems. I told you how to handle dependent sources. And that concludes the lecture.